Very good morning. Welcome to this third day of workshop. Today we are going to look at enablers. Last 2 days we provided you with reflections on our active learning based experiments that we are doing in IIT Bombay. We try to tell you how applications and active learning is strictly blended into teaching mathematical concepts. Because that is one of the most difficult part for students, and then how these elements are related. Digital tools, of course, are becoming increasingly very, very important. And one of the mandates of this program is to introduce you to different military initiatives on digital tools. Now, some programs like Tech are quite widely known. Most of the faculty members, students know about those programs. There are initiatives which are equally important or probably more important in terms of active learning, and which are being spearheaded by groups in IIT, faculty groups in IIT. And we thought of presenting those to you today. So one of them, of course, MOOCs initiative through NPTEL, all of you know. But relatively less known is virtual labs. Those of you who attended induction workshop in IIT Bombay, they were introduced to virtual labs by Prof. Noronha. But today they are going to learn something more as to how they can participate. Then we'll have a third lecture today on another initiative at IIT Bombay on developing a tool for flip classroom. So there's a tool developed called OG3, which is an open source tool developed by faculty members and students of computer science department. And the lecture today will be a blend of introduction to OG3 and flip classroom, because one of the developer himself is going to talk about it and how he uses that to teaching the course in computer science. So that is going to be so it's a mix of both, demonstration of OG3 and demonstration of how flip classroom can be used effectively in the class. Okay, let's short background for today's program, and then afterwards we are free to work on the project. It gives me great pleasure to introduce two of my colleagues, Prof.Santosh and his team manager, Pushpali. So this is a program, MHRD sponsored program, Virtual Labs, and both of them have been working for many years to get it to completely different level. Professor Noronha did his BTech from IIT Madras, and after that he went for his PhD from the University of Maryland. And after that, I think we did a postdoc with NIH, National Institute of Health in the US,
Then I came back. Then I came here.
And then after that, Professor Noronha has been with us in IIT Bombay. He works in biotechnology, systems biology. So his interests are quite varied. In our department, he teaches biology courses and data analysis courses and optimization and mathematics. So spanning over a wide spectrum. And he has been spearheading this virtual labs, and there is one more initiative in IIT Bombay, which is healthcare initiative, developing products for healthcare. He is one of the founding group members and guiding spirit for that particular program. Pushpali has been working with this team for almost 6 years now. Yeah. Prior to that, he was a faculty member in biology in Mumbai, and then he decided to shift to IIT Bombay and work with this team. And I think it's his effort which has, and guidance from Santosh has taken this project to completely new level, which, in my opinion, has not happened probably in other IITs or other projects. So it has continued much beyond what was earlier mandate of this project. So with this brief introduction, I will leave stage to them, and so they will tell you how you can be part of this new exciting project.
Thanks, Sachin. So, in some ways, as Sachin introduced, this is about how to engage in an active sense in a learning context. And most of you, as he implied, were already familiar with NPTEL. So, NPTEL is therefore, as far as you're concerned, the theory counterpart to virtual labs, which is the lab aspect of how we learn. Yeah.
Just one thing I want to add here. After I was talking to him about this new initiative which they are doing, is holding boot camps to encourage faculty and student groups to develop virtual labs. I realized that we participate in this initiative. There are multiple levels of activity because to develop a virtual lab yourself in your college, you have to form a team of multiple of students and faculty from multiple departments. Okay, which itself is collaborative learning which happens because of multiple students. See, because we cannot develop a tool that like this unless there is somebody from computer science, somebody from electrical, somebody from mechanical. They collaborate and come on one platform, and not just students, faculty and students come together on the platform. So this development process itself is an active learning, and then of course using it by the student to other level of active learning. So there are multiple levels of active learning involved here. I think you should pay special attention to this.
So, let me start by asking you folks. You've all recently graduated. I see that most of you are young recruits into your colleges, so you've all recently graduated. You've all recently handled labs. Either you took labs or you've been already in your colleges been running labs. Why do you run labs? So what do students gain out of a lab? Practical? To what? To? I'm hearing whispers. Well, you've got to be more precise than saying theoretical knowledge and practical knowledge. There's an end goal. There's something that you hope to achieve on having done a lab. Visualizing something, okay? Anything else? Okay, so you want to apply and learn something that you heard of in a theory lecture maybe, right? Is that the only reason? Because I heard something else there. You had a different reason for a virtual lab, not just to test theory. Why did you want a lab? You wanted some exposure to something. To what? To a concept? But you could have read that concept in a book, right? So what other exposure could you have gained by actually walking into a lab and doing an activity? Sorry? Applications of what? Solving a real-time problem, okay. Okay, but that comes back to testing theory. There's some theory and you're looking at the theory and you're kind of trying to work out whether the theory holds or you need some additional modification to the theory, right? So there are two practical reasons to do this. You are either interactively testing some concept, which is what you mostly answered. Most of your feedback was, there's some concept and you need to figure out a way to probe it and test to see whether it's actually holding, okay? But the other reason to get into a lab is to become familiar with real hardware. And for most of us who have never done things with our hands, we have never built stuff. In fact, we're told not to touch stuff because you'll break it, right? In schools, for the most part. For most of us, to even become familiar with what the real apparatus is itself exciting. And that becomes important if you want to be employed, especially in industry later on, where you will see the real apparatus. And if you have never been trained on the real thing, how do you expect to go and run a plant? Or, for that matter, optimize that plant? So two major goals. Now think back to the labs that you all have experienced. All of you have done, most of you are, as I understand it, engineers, a few from the sciences and some from the humanities. So especially for the engineers out here who have all done labs. By the way, are the labs normally held in the mornings or the afternoons? Why? Have you stopped to think why? After? Sorry? The mornings are engaged in lectures, but the lectures could have been held in the afternoon. You could have had the labs in the mornings. Energy levels are high in the morning. So the labs were therefore designed to keep you on your feet so that you not fall asleep. Is that what you're saying? Okay. So notice that right there, in a subconscious sense, the educational system has given less value to a lab compared to a theory lecture. It's in an afternoon. It's in an afternoon after a heavy lunch. I'm assuming that your hostel lunches are good heavy lunches. But it keeps you on your feet. How long? How long is that lab experience? Why does it have to be 3 hours? Why was it important for a lab experiment to be 3 hours long? Okay. Now think back to any lab experiment you did and ask yourself, what fraction of those 3 hours were you actually learning something? Not a lot, right? If it was an experiment, for example, which involves changes in temperatures, you kind of sat around waiting for a temperature to hit a new steady state. If it was a fluids experiment, you were typically waiting for a bucket to fill up with fluid so you could measure a flow rate. That was very low level of learning, if there was any learning at all that was happening in the 3 hours period. So to be critical about the process, if you think back, that whole afternoon experience has been designed to keep you out of trouble in a lab, and essentially your college was babysitting you. I'm being critical, but that's the reality of it. So most colleges end up trying to keep students out of trouble in the afternoons by offering them very poor lab experiences, where neither of those two things is going to happen. Do you see real apparatus in a lab? Very unlikely. Because there's too much of a danger that if you're just feeling really jobless and reckless, that you might go and tamper with real hardware and destroy it. And that's an expensive business for a college to maintain such things. And if you wanted to test a concept, did you need to take 3 hours to test a concept? How could it have been done in 5 seconds? If it was an equation that you were testing by trying to collect data and then plug it into that equation to see whether indeed the theory worked out. So structurally, the way we have gone about trying to run a lab is all wrong. So before I go to the next slide, you get a sense now that the way labs are run is not great and we ought to be doing better. But at the other extreme, what do you think is an ideal lab? What should be an ideal lab? So what does it take to achieve this? If I need you to be familiar with how to operate hardware and learn how to do things with your hands, and at the same time, if I need you to think about theoretical concepts and test them, which basically means you'll have to generate some data from your apparatus, what does it take? So what it takes is that you're going to have to be given a concept to test, but then you're expected to walk up to a storeroom of parts and you build your lab experiment yourself. You've got to be able to build your own apparatus. Okay? And then you generate your own data. And then you confirm through some analysis as to whether your data confirms or, for that matter, denies some theory. Do you need to modify the theory or is it okay? Okay? And then finally the hard part, take the whole thing apart and put away the parts in a storeroom. which is of course something we never do. And why do we not do it? Because we cannot afford to do it. Most of us cannot, most colleges cannot afford to do it. In fact, very few colleges, even in the US, the top colleges in the US would even think this way. Because it's a risky business to allow students and armies of students to go and touch components in the storeroom, because they'll pretty much destroy half of what they see. But this is what it takes to learn. And the long-term context has to be that this is what we do, even if it's an expensive process of doing things. I'll come to this at the end, because it turns out there are cheaper ways of doing this now, especially in the new world of digital prototyping. We don't need to buy expensive systems and hardware parts. So my talk is not on hardware labs, but this is what we really ought to be doing. And as a stopgap arrangement, because we cannot afford to do this, an intermediate solution being proposed is virtual labs, which is simulators. But I start by saying training engineers on simulators cannot be the end of the story, because you really do not want people, it's like a pilot, you don't want pilots to be trained only on simulators, you want them to actually go out and fly a plane and learn how to fly a plane by gaining actual experience. It's the same thing with surgeons. You want them to learn how to practice on simulators and then actually go and perform a few operations and then get certified as a surgeon. Same thing with engineers. So there's a certain element, it turns out, which you can fast track if you use simulations. That's at an active learning level that you engage. But there's no shortcut to getting the real world experience of playing around with hardware. And that's left for individual colleges to figure out, given their resources, given their funding situation, and given their enthusiasm levels to play around with hardware. So the reason most physical labs, and so the real hardware labs are now called physical labs, the reason they don't happen is, for the most part, equipment is not available. In fact, for the 3R experience to happen, think of the apparatus that you have had in your individual colleges. For the 3R experience to happen, that entire experience was done in some rig, which is customized so that things will happen in a short period of time, in 3 hours. Why are we saying that a lab experiment must happen in 3 hours? Why not 8 hours? Why not 24 hours? Right? If it were to be a biology experiment, things happen very slowly. If it were to be an electrical engineering experiment, things happen very fast. You don't need 3 hours. So why are we locking people into 3 hours as a slot? Right? So therefore, if you want to fast forward certain things, or on the other hand, you want to slow down certain things, people have built apparatus of certain kinds, rigs, which you can purchase, which now allow you to do experiments in short periods of time. But now what happens as a mentality, even at IIT Bombay, in our department, for example, is these rigs are expensive, and we don't want people to touch these things. We don't want students to touch these things. You walk up to it, press a button, collect some data, do something with the data. Don't mess with the hardware. And that entire experience was designed to operate at a scale where you'll generate data fast and get it done in 3 hours. When the real world process may take 24 hours, which means, remember my 2 objectives for a lab: be exposed to the real world hardware, be exposed to the concepts and how to test the concepts. Maybe you got to test the concepts, but you have not managed to get a feel for the real world hardware. So we fail in that context. So equipment is either not available, or if it's available, it's locked down. Have you ever wondered why the lab must occur only between 2 and 5 p.m.? Could that lab experiment have been carried out middle of the night? Is there a technological reason why it cannot be done? Right? So if you're implying that people are alert in the morning, people are, at least our students here tend to stay up all night and they're most alert at night. So can we get them to do lab experiments in the middle of the night? Why not? What does it take to get there? Right? You'll realize it's actually administrator mentalities. We don't want people randomly walking into our labs in the middle of the night because we don't know what nonsense they'll be up to. And it starts there. So at one level, there's this element of trust. You're going to have to trust people to correctly use stuff. Yes, there'll be some abuse, but there's a bigger picture. You're training people, and that's the whole purpose of a university, right? You're training people to do stuff without risk of something blowing up in a big way, because you will not be allowed to learn in this fashion in industry. So this is the place to try these things. So the basic idea, therefore, is that in a virtual lab, either hardware or a simulator is located somewhere else, far away. And I'll come to this idea that even hardware can be deployed, for example, in the middle of the night, and an experiment taken on hardware remotely, and you can generate data through the net, and you can learn and test a concept. When MHRD asked us to think about virtual labs, one of the reasons it asked us is obviously there's a huge amount of money given to the IITs to set up good labs. At which point the question got asked, why are you guys using your labs only from 2 p.m. to 5 p.m.? Is there a way for this hardware to become available to other people, for example, students from other colleges, after 5 p.m.? And the answer is yes, technically it's possible. We have to put in sensors, we have to enable some IT, data must go up and down, you must stream data to a student sitting far away, you have to worry about the security of all of this. And if the student must be given access to the controls on the hardware, figure out a way to give them controls. So in theory it's doable, and we did play around with some of this, which is why we say that it's possible to actually make better use of hardware by allowing people to use it 24/7, right? Technically that comes down to give people slots of time. So give a student a 30-minute slot, and within a 30-minute slot you have to log in, access the hardware, generate some data, hope that the net doesn't crash somewhere in that 30 minutes. If it does, maybe you have to give them a fresh slot, and so on. All of that, there may be issues, but they can all be solved one by one. Is that a great solution? It's better than nothing, but it's still not giving them exposure to the real hardware, right? And then there's another problem with having what we call remote triggered physical labs. The big problem is only one student can control a piece of hardware at one time, whether they are local or whether they're sitting remote. You can hand off controls to one student at a time. So it doesn't scale. And when MHRD says, figure out a way in which 1 lakh kids across the country can learn a particular electrical engineering lab, how do you do this? You can't be allocating slots on hardware one at a time. You can play tricks. You can allow one guy to control the hardware and then have 1,000 other people watching. But that's exactly what happens in the physical lab. So when you form teams of students in your physical lab, 2 to 5 p.m., what happens? 4 kids, 5 kids are sent to a particular apparatus. And then what practically happens in terms of learning? 1 guy is doing the work, 3 guys are watching, goofing off. So again, there's a problem. So the moment you allow 1 guy to control hardware and 1,000 people to watch, most of them are not learning, because there's no incentive for them to learn. So if you work, therefore, through the line of thought, the only way in which you allow for people to test concepts very rapidly at scale is through simulators, because it's possible for me to allow 1,000 simultaneous uses of a simulator, but I can only allow 1 access of hardware at a time. Okay, so that's the background to our basic idea in terms of virtual labs. And if you look at virtual labs, essentially they run as simulators of various concepts at various levels of sophistication. In some cases, they are very basic cartoons just trying to interactively prove some or test some theoretical concept. Some of them have evolved over time to almost be like flight simulators. So they are immersive experiences. You can sit in them and you can design tasks in them. Just like in a flight simulator, you can simulate landing at different airports. So there are different challenges to the test pilot. Similarly here, you can build, for example, in electrical engineering, if you wish to teach people the basics of circuitry, there are simulators available to you as platforms, technology platforms, and now you construct different tasks, get them to build a particular circuit, test it, and that's obviously better than doing it in real life and blowing up things, right? And you can see a learning model where you simulate and test to see what happens if you assemble different circuitry, and when something works on the simulator, you say, let me go try it out in reality. That's somewhat easy to do in electrical engineering. Why? Because the technology platforms exist. The circuit simulators exist as generic platforms. If I were to try to do this in civil engineering, that's hard to do because we don't have such software platforms where you can simulate various structures, for example, right? There are platforms, but they're proprietary. Now, another thing that happens here is if you look at an electrical circuit versus a civil engineering kind of experiment, the difference between a simulated circuit, the way a simulated circuit behaves, and the real circuit behaves is negligible. What that means is the theory is so good and the theory has been programmed so well in the simulator that you'll more or less get what you predict as a simulated output is more or less what you'll see in the real world. But that's not true with civil engineering experiments. That's not true with chemical engineering experiments. I can simulate a distillation column in chemical engineering, but when I do the real experiment, my data is going to be off. Okay? But rather than get concerned about this, active learning concerns itself with why is it off? If I don't get a result that's predicted by theory, you don't start blaming everything. You don't start blaming the apparatus. You don't start blaming the student. You instead flip it around and ask, why is there a deviation from that simple theoretical equation that you captured in the simulator? And one of the things that happened to us as we built our simulators, these kinds of simulators, is our understanding of theory itself improved tremendously. Why? Think of this. If I ask you to take an equation, y is a function of x, and you're given a setting for x, you can obviously compute y. That's a textbook example. And I can implement that even in a simulator form. I give you some simulator, you choose some settings, you'll get some output. But if I give you that same simulator, I give you x, you try to compute y, and then I give you the real y, which I've gotten in a lab, and you find out they're different, and I now ask you the question, why are the two values of y different? What are you going to do about it? Right? And how do I build in, therefore, clearly my simulator is not capturing the real world. What are your options? Either you just blame various factors, like as I said, you blame the apparatus, you blame the student, and so on, which is what we usually do. Right? Or else, you ask the question, what is this deviation from ideal theory which is occurring, which causes this deviation in my output measurement? And that question of what is this deviation, because you're going to have to build that into your simulator if you want to make your simulator more realistic. That process of asking what is that deviation is the most enriching experience you will have. This is when your actual understanding of a subject happens, not simply y as a function of x, plug in x and get y. That anybody can do. But for you to be able to explain why a deviation starts happening, what are the multiple possible causes, and which of the multiple possible causes actually happens to be an issue, is the most enriching experience. I have some slides on some of these things, but let me talk through one example in chemical engineering, because that's something which started off the virtual labs process 5 years ago as we started building simulators. So when MHRD asked us to essentially create virtual labs, where they were, by the way, where they were going is, the only way they saw themselves being able to scale lab education in the country was by creating simulators. And they asked us to, therefore, map the current undergraduate experiments that we were running at IIT into simulated form and offer them to other colleges. I'll explain the logistics of that a little later, but let's take one example. In chemical engineering, we have a simple experiment of fluids flowing through pipes, and we ask the question, can we work out things like friction factors and so on? And this is a very basic fluid mechanics concept. In fact, it would be of use in mechanical engineering, aero, and so on. There's finally some equation which says F, the friction factor, is 16 over Reynolds number. 16 is a magic number. You can prove it from theory, first principles theory. We, in our undergraduate physical lab, have an apparatus where we have a pipe. We have the ability to push in different fluids at different flow rates. You can collect them, you can measure pressure drops, and finally from all of this, you can compute a friction factor. And again, the objective is to check the friction factor versus different Reynolds number settings and figure out whether we are going to get that magic constant, 16. And if you do the experiment in our lab, you will get, instead of 16, you will get 160. At this point, every single textbook as a basic piece of theory says 16 is the magic number. So that is not disputed. In fact, you can theoretically prove that 16 is the right number. So then what's going on? Why are we seeing 160 when the textbook says 16? Right? For years in the physical lab, our students in their lab reports have ended up saying the hardware is defective. The pressure drops you're measuring are wrong. The least counts of whatever manometer are terrible, and so on. So you blame the hardware, end of story. Batch after batch after batch. Hundreds of batches. The same answer, the hardware is bad. But why do we get, even if the hardware is bad, what's causing you to get 160 versus 16? Because you see, the point of active learning is then ask the question, if something's bad, what are you going to fix? What thing in here is defective that you can fix? Is it a measurement? Is it a sensor which is bad? Is it something about the way the fluids are being introduced which is bad? Right? That theory, by the way, holds for laminar flow of fluids, when the flow is very gentle and smooth through a pipe. And if you look at our setup, it's clearly not smooth and gentle. There's a lot of turbulence happening. If the flow were to be turbulent, what constant do you expect? Do you expect 16? Do you expect 50? Do you expect 100? Do you expect 160? And at some point, there is some theory, we're not teaching it, but there is some theory in the research literature which says that if you took the same apparatus and put a turbulent fluid through it, you would get some other value. What is that value? Right? Why did we get into it? Because this was a 3-hour experiment to figure out that the number that you experimentally get is not the number in the textbook. When I try to create a simulator, what am I going to do? I'm going to create some artwork like this. There's a pipe. I'll allow you to press a button, fluid will flow. You will simulate different flow rates. You will measure pressure drops. I'll show you a manometer, levels will change. And you will measure that distance and from there compute a pressure drop. You can play tricks like this. But whatever stuff you do on this, a student will spend 5 minutes at most on this and compute that constant. What is taking you 3 hours in an actual physical experiment? In 5 minutes, you can test this constant. And now I have a problem. If the objective was to keep the student busy for a period of time, and that's why we are doing the lab, my whole activity is done in like 5 minutes. How do I keep that student busy even more? The only way I can keep the student busy is by asking them a higher level question. You pressed buttons, you read off measurements, you computed your constant, turns out to be not 16, therefore now my next immediate task that I give you is, what in here would you change in terms of theory to come closer to the experimentally observed value of 160? What happens if you insert a turbulent fluid? But now notice I have to do some more work as a teacher, as an instructor. Why? Because I have to capture the theory of turbulent flow through a pipe and make sure my simulator knows about that insight. Because the student next will be expected to press more buttons, choosing turbulent fluids, and then they must see some settings change in terms of pressure drops. They'll have to back compute things from it and work out a constant. This is not textbook stuff. We ourselves have not studied this stuff. But the act of creating a simulator and realizing that you have to not just throw some random number out there to that student as a constant, but to make it a more enriching experience for the student requires us to learn the theory so that we could teach it to somebody else, so that the simulated experience could be rich enough for somebody else. What happens if the flow is not fed straight? What if it's coming in at an angle? How much of a deviation can we expect in everything that we are measuring? What if we don't assume that the pipe is smooth? What if the pipe is rough? What's going to happen then? Each of these requires you to read up some theory and build something back into the simulator to make it more and more realistic. It's like saying, let's build a flight simulator, and the first thing you would do to show an airplane is draw a line, draw 2 more lines to represent wings. At some level, that's a simulator. I can make that move, and I can teach you stuff about the basics of flight using such artwork, sticks as artwork. But how do you go from there to the actual flight simulator where the pilot learns how to fly in various kinds of weather and land on different runways. So you can see there's a whole level of enrichment that you can perform systematically, where you say, let me build in some basic concepts using some basic artwork. If you look carefully, the one on the right is very basic artwork. And there's certain concepts that are conveyed using just this. This is not the real apparatus. For sure, you're not going to see stuff like this in reality, but it conveys a concept. But I build on this and I make it more and more rich. You can see on the bottom left, essentially, I think that's a biology experiment where you're trying to explain to students how to go about doing the basics of transfer of organisms from one vessel, a flask or whatever, to a plate and so on. So you're giving them some understanding of what might happen and what might go wrong if they do it the wrong way. Okay, that's starting to be a little more realistic in terms of the apparatus you might start seeing. At the top left, you're seeing something even more realistic, because that's actually an abstraction of the real apparatus with the real control. So you press things and you get things done, like you would press them on the real machines, right? So this business of bringing in more theory and making the entire experience more interactive and more rich is ultimately what we want. Yeah. So just to summarize broadly, when you talk about virtual labs, you can do this at multiple levels. You can just simply take some theory, put it online in some encoded form, and you can hit students with questions based on the theory. But that assumes your theory is rich. If it is just y equals f of x, it's not rich. Because somebody that's what you do in an exam. You just give them a simple set of equations and ask them to compute something. So how do you make it more interactive? To make it more interactive, you have to ask them questions. If I were to change this, what's going to happen there? And by the way, if I change y, what's going to happen to x? Not just changing x and asking what's going to happen to y. So the same theory is the sort of thing you can approach from many different perspectives and ask, what happens when I change this? What happens if my measurement here is off by 10%? What will that do to my output? Each of these becomes a question that you can ask. Okay. The second way we have learned how to do this is to actually use our real hardware, generate data sets, and then randomly feed these data sets to kids sitting elsewhere. So the advantage is this is real data. Like I said, in some disciplines, you don't have the advantage of seeing highly ideal systems. There are non-idealities, in which case simulating some theory and giving it to them is going to expose them to the fact that the real world is quite different. So the next best thing is generate your data sets, give it to them, ask them to compute things. That's the intermediate level, measurement-based labs. And then what is the hardest to do is to build hardware and let people remote trigger it. Professor Kannan, I believe, is giving a lecture tomorrow, Friday. So he might talk about something that he built as a remote trigger device for essentially teaching people the basics of process control. And at the core of it, what he has is a heating element which generates some heat, and you can control the power to it, and in that sense, the temperature it rises to. And then he's got a CPU fan, and you can control that as well, and that becomes a cooling system. So you can heat and you can cool, and now you're trying to keep at a set point. Simple hardware, but you can learn a bunch of things through it. You can test different algorithms for control by trying to get it to maintain a set point. He calls it a single board heater. But getting somebody sitting far away to control this is problematic, because you try to control something and then the net goes down on you, there's a problem. We had a similar challenge. We tried to build a reactor and we tried to let people control the reactor from a different location. In theory it works. The moment the network goes down, you realize your reactor is spinning at top speed, and that's not a great thing for hardware to run at top speed. So it now forces us to reset the hardware the moment we realize that the network has gone down. And it turns out it's a solved problem. If you take our local trains, there's something called a dead man switch. If something happens to the driver of a train who has a heart attack, you can't allow the train to keep going at top speed. So the moment the driver falls sick and takes his hand off the handle, the driving handle, the train comes to a halt. So in a similar sense, the moment we realized we had to build such thing, the moment we sense that the network's not up and running, reset the hardware, because otherwise it's unnecessarily going to run, and the other student is not anyway seeing the data that is being generated. Yeah, so there are all kinds of challenges. Next. So just to give you screenshots of how an experiment would be structured, do you realize that on the left, you're doing what you're doing in a regular lab? On the left panel, you see an aim, there's a pre-test, okay? There's some theory. Then finally, you take people to the actual simulator tab where they do the actual experiment. There's some procedure that's kind of written there of what you might want to do. Then there's a post-test. I evaluate you after you've taken the experiment, okay? One of the problems with why labs are not well organized is because of the effort of an instructor to sit and personally engage with students one-on-one. And now the challenge is if you're trying to do this using a simulator, how do you evaluate kids for taking simulated experiments? And you're kind of forced into doing a pre-test before they even take the experiment. What do they understand of the concept? Having taken this experiment, what do they now understand? So the difference, pre and post, is a demonstration of what they've learned, right? So you realize you've got to structure a lab in these fashions. So what is a pre-test, what is a post-test? And I'll show you snapshots of this. Notice that we are also throwing in on the left reference material. The same way we learned that a simple flow-through pipes is actually much more complicated than simply asking F versus Reynolds and trying to work out 16. That we have to read more theory that will explain other scenarios, which is why the real world data will end up not giving us 16. So all of that is only the sort of thing that students would learn if you give them more learning. It's like a Wikipedia page. Read the basics, but then you need more links to more advanced material. So that's that reference, yeah. So just quickly flipping through, you see the various tabs for, in this case, a particular fluids experiment again. Yeah, keep going. So in this case, this is not even a sophisticated piece of artwork. Do you see that all we are giving them is a slider? Change the setting of something. If I wanted you to just learn about a concept, and I'm not fooling you, I'm not pretending that I'm showing you the real world apparatus. This is not artwork demonstrating the real world apparatus. But I just want you to learn a concept. I want you to test a concept. I just allow you to change the settings and ask what happens. That's enough. Already the level of learning of a student is at a higher level. I asked you when are the labs held, you answered in the afternoon. But do you realize also that labs are normally not held in the same semester as the theory course? At least here they are not. Usually the lab for a particular concept is held in the following semester for us. And there's such a big gap between theory and lab experiment. You're going to hear about MOOCs. The future of lab education is you're going to be watching 15 minutes of theory. Think of NPTEL. Instead of NPTEL being a 1-hour lecture, NPTEL is about to be redone in small chunks. So think of watching a 15-minute video of theory, and then what should you be doing? You should be taking simulators, testing out that theory right then and there, not one semester later. And ideally, you're using these simulators in a classroom while you're teaching the theory. Right then and there, not later on. The later on is because we cannot physically do it, so we force you to come to a lab in the afternoon. And because logistically it's not easy to do it in the same semester with the same instructor, we end up pushing the lab to the next semester. So think of something this simple. Why would you not be able to use it in your own teaching? Where there's some theory, and you've derived some theory, and now you're asking what happens as I change some settings. And you can make this more and more rich till it finally looks like the real world system in terms of apparatus. So again, notice that this is very basic artwork, but in this case it proves a concept. Next. Keep going. Yeah. This is a similar experiment, but this time deliberately I've taken an experiment created by not IITs, not one of the IITs, but this is a college in Pune called PVG College of Engineering. And the developers are people like you. And we've worked with them and we've created content. Yeah, next. In this case, again, you can see the structure on the left, the panel on the left is more or less similar. So we worked with them, explained to them why they need to design experiments of this sort. And in this case, this is just about computer graphics. How do you draw lines on a screen with pixels, and again keep flipping through. Yeah, keep going. So there are different algorithms which will draw lines in different ways, and now you can pose all kinds of tasks to students. Okay, keep going. Yeah. So in this case, yeah, go to the previous one. So in this case, you're rating students as to whether they understood the theory as to how the line is to be drawn across pixels, and you're asking them to choose the pixels which will be highlighted when the line is drawn. And if they're doing it wrong, you can give them immediate feedback on why they've done it wrong. So theory, immediately do this. This is not a complicated piece of things. This takes 10 minutes for somebody to do in a classroom. And everyone can do it individually. One of the talks you're going to hear about is Bodhi tree later on. Bodhi tree, the whole point of it is just find a way so that you have a learning management system where everyone can log in and the teacher can monitor the students trying to do one of these things. Because I need to know who's doing it, who's gone off to sleep, who's not, whatever it is. I need to know who's doing it fast and who's taking a lot of time to do this. Because I need to probably give that student more attention. All of that becomes available if there's a way for you to get some data capture from the student about how they're performing. Which comes back to you need to give them some activity to do online and you need to find a way to monitor it as it's being done. So today's enabling talks are how to create content. When the Bodhi tree talk happens, that's basically about what's the platform in which this content will get hosted and how will you then administer it, how will you monitor it, right? So in summary, therefore, all of that we have talked about so far. Finally, there's going to be a complete learning management system. MHRD has already announced to us that they're thinking of a virtual university. And where it's going is obviously they cannot create more IITs, they cannot create more NITs and so on. And so with whatever money they have, and they've recently announced an education policy, for higher education, almost surely they're going to invest a big pot of money in what's called a virtual university. So what's a virtual university? They basically invested historically a lot of money in NPTEL. A lot of content got created as NPTEL. All of you are familiar with it. But NPTEL by itself is not enough. Similarly, they invested a lot of money in lab experiments, creating simulators for lab experiments. Now they're asking, can it all come together? Can a given student log in into some central portal as a virtual university student? Can you watch your video chunks like YouTube, small chunks? Can you watch the theory, do the experiment, watch the next bit of theory, do the experiment, keep going. And you learn at your own time. Why are you learning 9 to 5? You learn at your own time, learn at your own pace. Not as easy as it sounds, because how are you going to evaluate somebody who's sitting at home? How are you going to certify that they did this? There are practical challenges, but we're getting there. One by one, we are tackling all these things. But it will happen. And obviously, a major element in making that happen is create content, create good content. Create content which is of use to universities and colleges throughout the country. Okay? So these are obvious things in terms of what are benefits. Next. But you'll realize students also are very enthusiastic about this. The students would obviously prefer to sit at a simulator and answer questions about a concept rather than spend 3 hours in a lab. Okay. Next. So when the MHRD, so this is a bit of the history now of the program. We are 6 years old as a project. In that sense, we are much newer than NPTEL. There were 11 participating institutes initially. IIT Delhi is the lead institute. But each institute here kind of took a zone in the country. If you look at the map, you'll realize they're spread out all over the country. So for example, IIT Bombay now runs the western zone in this country. Yeah, next. And we all started creating our own content. All these simulator snapshots that I showed you, we all independently created stuff. And that doesn't work. A student only gets confused. If I tell them go to the IIT Bombay website and take an experiment or go to IIT Delhi website and take an experiment, that's confusing. So finally we created one portal called vlab.co.in where there are labs which are created by a bunch of developers, all commonly hosted on a central platform. For the moment, it's all free. In terms of timelines, we started with an initial challenge of creating 10 labs as a proof of concept. That worked so well, immediately it escalated into a main phase program where they asked us to create many more labs. So when I say a lab course is typically, when you think of a lab, it's usually some 8 experiments in a semester. So we initially did that. So we said, let's create labs, just mapping what we are physically doing right now into simulated forms. We just did that. And if you look at what's happened, after the main phase, again a repeat phase, main phase 2 we call it, created more content, and at this point the emphasis on how do you give it to people? How do you make sure students are accessing it? Don't simply create stuff. Okay, so that's rollout, and I'll explain rollout even more. So finally MHRD gets interested, and I guess it's an economic argument. They'll be interested in how many students learned how many concepts and what is the expense involved. Finally, is it worth it? So it'll be some financial argument. So outreach, what is outreach like? And in what is the latest phase which we control as a zone now, we're now talking about how to get a community of people to create content. It's one thing for the IITs to create content, but at the end of the day, our syllabus is not your syllabus and vice versa. And there are subjects that you're teaching which you're not teaching, where you should be creating content, not us. So how do we get, having kind of understood how to create content, how do we now get a community to create content? That's the current phase. And on the right, yeah, go back just a minute. So on the right, you will realize that we're already talking about people like you creating experiments. And 113 experiments have just recently been created. Yeah. If you look at the coverage of disciplines, they span the basic engineering disciplines. You will realize the big bars: computer science, electronics, biomedical engineering. And biomedical engineering is again mostly data science. Is that logical? Those are the disciplines in which we have the most labs. Would that make sense to you? It should. The reason is, those, if you remember, I told you, those are the disciplines where you have access to lots of open source freeware simulators. I want to design circuitry, you have access to electrical engineering softwares for that. So it became very easy to adopt those things and to create activities on those platforms. Whereas if you look at mechanical engineering, civil engineering, chemical engineering, they're terrible. Because people did not sit down. People saw a big barrier to even how to create stuff which might be open source. So one of the mandates, I forgot to tell you, the mandate here is it should be free to access to anybody, at least at this time. Which means you're forced to use free software, because I cannot put proprietary software out there, because finally if it were proprietary, I have to pass a fee onto a student. So we have 9 disciplines, and it's going beyond engineering, it's getting into biology now. Can chemistry, go back once again. So we're looking at 114 labs, but something else that has happened is we have realized these labs, a lab is not a unit of development. Why? Because a chemical engineering fluids experiment is just as useful in aero, it is just as useful in mechanical, right? And we realize it's getting to the point where people are borrowing stuff from other places and using it in their own teaching. So at the core of it, create experiments. Who uses that experiment, why they're using that experiment is their business. So create content as experiments and let them assemble their own lab. Take experiments from different disciplines, from different labs, and let them assemble their own simulated lab. Yeah. If you look at how we have gone about rolling this out, our methodology has been to, in each of our zones, so as I said, we are in the western zone. So we have created a collection of nodal centers. So we are under pressure to reach out to all colleges in our zone. But we cannot do that logistically. So our method has been to ask neighboring colleges to come up to us, show some interest in this. The ones which show a lot of interest, we appoint as nodal centers and we spend time with them. Okay? You're seeing a nationwide map of how we are spread out. So other than the northeast and to some extent in Rajasthan, most of you are from Rajasthan, we managed to spread out well. So we have very good presence already in, we got a huge presence in Maharashtra and Gujarat right now, but not in Rajasthan. And that's mostly for logistical reasons. It's been easier for us to go up and down locally here and get things done. Yeah. Our map, IIT Bombay itself as a portal. So you see that we are spread out well locally. And if you look at our numbers, we initially started off with about 20 nodal centers in 2016, but notice how it's expanded to 110 nodal centers as of now. That's 110 colleges already talking to us all the time about using content. I know for a fact that's making a difference to these colleges, because many of them are starting to advertise virtual labs on their websites. And it's definitely impacting their admissions. So there's large numbers of people obviously being impacted by this, right? Yeah. So let me, at this point, kind of deviate and rather than talk about pedagogy and learning, I'll come back to that at the end. Let me talk about the process of what we do. So we first invite people to, so this is, so what one of the things to appreciate here is, and that's also the philosophy of TechWhip, is we are building relationships with colleges. There are 4 colleges as I understand it here, 4 or 5, right, as part of TechWhip, the TechWhip scheme. And what we're looking to do is to get enthusiasts in these colleges to associate with this. You have been chosen to be part of a TechWhip program, but chosen to do what? One of the things you can do is to actually participate in creating content. If you're going to create content, what's the pathway? How does it happen? First, normally we go out and we run regional workshops. That's because we simply, just like this as a workshop, we run such workshops elsewhere just to get people used to the idea of virtual labs and, for that matter, other technologies. Then we formally ask for an expression of interest, and the trick here is basically we are trying to get management to ensure that you will get access to resources to run virtual labs at your end. So do this as a formality. We get a formal letter, we write formal letters to your principals and department heads. Why? Because down the road you will, for example, need control over a computer classroom if you're going to show simulators. You need to be able to hold events at your colleges where you're running events for your students, or for that matter, neighboring colleges. In fact, the expectation is Nodal Centers first learn how to run virtual labs, and then they start running it not only for themselves, but for the neighboring colleges. So the Nodal Center therefore becomes a central location in a given city. Right? So typically a coordinator is appointed at a college from whichever discipline, and coordinator is, from our perspective, a high energy person who will potentially go up and down and run events locally at the college. We call these rollout workshops, where people essentially use content that's already created. Not necessarily created by IIT Bombay, use content created wherever. Yeah, keep going back, go back. Okay, as I said, they ought to reach out to neighboring colleges, and then there's a periodic interaction with the coordinators trying to understand what's happening in terms of rollout, and whether essentially there are some pain points. In some colleges there are problems trying to get past administration, trying to get access to resources. So we work with them on those. Next. But this is the exciting part. If you remember, the latest phase of virtual labs was to create content. At this point, I'm not saying create content in electrical engineering, mechanical engineering, whatever. Create content, create interactive content in anything. Just to let you know, we are creating interactive content in how to train nurses to do things in villages. That's a healthcare program. But the methodology that I learned in virtual labs will apply for even how to train paramedics. It will apply with how to train polytechnic students. It's a teaching style. It's a teaching approach. And you can teach anybody with it. Okay? So therefore, there's a certain process that we now engage in with how to create content. We call that, so that involves what are called workshops and boot camps. Okay? And I'll explain each of those in detail. But the intent is to get you to create content, get you to use your own content for your own teaching. But because this content has probably been created with open source materials, the ideal situation is you're now offering this content to the entire country to use. So PVG's content, I showed you that computer graphics lab. That content is about to become part of the national virtual labs pool of labs. And the obvious benefit for them is they're going to get a lot of publicity for it internally, for having created content which colleges everywhere over the country will use. Okay. There's also this element that students will participate in these activities in a big way in terms of actually creating the simulators and doing a lot of the coding. And that's turned out to be beneficial because clubs of students are forming in all these colleges which are partnering with us. And that's a lot of energy, because when students come together with faculty and do stuff, more things will happen, not just virtual labs. And some of these students, we are actually getting to the point where we are realizing they're really talented, and we're bringing them this year. How many? Yeah, we were probably taking 10 to 12 students this summer to come in here and actually work out of here on projects. Yeah. So at this point, the content that we are collectively developing with colleges around us is not directly sitting on the national portal. It is sitting on what we call a developmental portal. So we are developing, we're testing it, we're making sure there's a quality check on it, and then finally we are handing it off to the national portal for formal large-scale deployment. Yeah. So we created a community portal where you will learn the basics of how to create a virtual lab experiment. Yeah. Why did we need to do this? Because we realized there's such a huge demand for content creation. If you just look at the number of universities out there, and each of those has its own syllabus finally across the various disciplines. So how do we create this much content? Yeah. I put the slide up, but really the fact is, even if I've created 1,200 experiments, it's not covering the entire syllabus that a university has. There are gaps. And these gaps are because there is, for example, a difference between what the IITs teach and what colleges teach. Which means, finally, if the gaps have to be plugged, we can't be coming and creating theory for you. You create your own theory. Which is why it's more useful for us to sit with you and explain to you how to create your own content, because the long-term payoff is big. You will not only create one or two things, you will create hundreds of things long-term. That, as I said, has already started with a few partnering colleges with us. Yeah. So PVG demonstrated the first set of pilot experiments in 2016, but several other colleges have now joined in. And I think in some ways, many of them realize that this is the future where they collaboratively create content with us. It's not for us to create content and dump on you. And the honest fact is, many of the things that we created and gave out were not of high quality. And colleges understand that. So one of the reasons we ask for rollout workshops to happen is you will figure out what content is available online. It's like you going to YouTube and hunting around for a video to learn a particular concept. There are good videos, there are bad videos. There are good virtual labs, there are bad virtual labs. But when there's a bad virtual lab, you don't sit back and say there's a bad virtual lab, you fix it. To fix it, you need to learn a few basic tools of how to program, what are the specifications of an experiment, what is going to happen to that experiment once you've created something, how is it going to be hosted. And that's a process that we explain in boot camps. Yeah. So the number 113 that's going on, 113 was created in the last year, and you have to contrast that with the 276 experiments that we're expecting the IITs to create. 113, but I don't have a number here. Pushpadeep, you might. The expressions of interest for creating experiments by nodal centers, what might that be? 1,500. Do you see that? Colleges want to create, at the moment, 1,500 experiments, which means they'll do far better than the IITs. The IITs at best can create 250, 280 experiments. Which is why our energies are now being spent on how to work with the colleges and work out a pipeline by which they can create the content that they want to create. And we are under pressure to explain to them processes and methods of this. Yeah. So they're all over the place. If you look at now the kinds of lab topics, they're ranging over all kinds of things. Of course, again, an emphasis on engineering. But there's no reason this cannot be done in biology, in chemistry, even in the humanities. So we started running workshops because we realized that rather than try to do things in-house, we needed to spend time elsewhere. So we've been going around doing workshops all over the place. Recently one was held in Aurangabad, and in these workshops we give lectures, but we also interactively sit with people. So kind of like we expect to, as I understand it, run these projects this afternoon and so on, where you're going to have to demonstrate that you've learned the elements of active learning, right? So you're going to come up with some storyboards that understand. So similar things is what we do there. It doesn't happen just like that. It's not like we turn up and suddenly people sit down and create virtual labs. There's a lot of preparation before we even come in. Teams are created and so on. Ideas are chosen. Topics are chosen. Okay, technologies are chosen of how they're going to go about it. And then finally, in a high energy 1 week event, literally there are people who have worked 24/7 in some of these things, the kids especially, we get this stuff done. Yeah. So Marwadi University, yeah, Gujarat, MIT, this was very recent. So large numbers of people at a college. One of the things we have done here, and this is important, to reduce the barrier in how to create stuff. If so many people are already creating stuff, the question is, can you recycle some of the stuff already created? You have to create everything from scratch. And the answer is no. It's open source. By definition, if it's open source, you're allowed to take it, reuse it, make another lab out of some of the artwork, for example, as long as you give it back to the community. Okay? So we have created a repository in which all these codes are being stored, because that is a long-term resource itself, so that people can. So when somebody says the lab, the experiment that's available to me online is not great, you have the codes. Go and add a feature to it and make it better. Don't wait for somebody else to do it. Okay? Yeah. So the boot camp is a very intense event, and when Sachin at the beginning of this indicated that there's a boot camp structure that we operate, one of the things we potentially can do for you is run a boot camp in Rajasthan, similar in structure to these things, where okay, we take participants and create teams out of them. So I understand teams have been created here already for the projects that you're doing. We have a slightly different notion of what a team is. To create a simulator for your own teaching, what do you need? There's an instructor at least, maybe more than one instructor in a team. Then you need some people to sit and code. Students. We realized that having students all from the same department was not going to be useful. The same way, when you take 4 students and ask them to do a lab experiment, it doesn't work out. 1 guy is working, 3 guys are watching. So you need to create a student team with different skill sets. There's somebody who's good at creating a storyboard. It's like a movie. Finally, you're making a movie. So you need different job requirements in making that movie. Somebody who's good at a storyboard. Somebody who's a script writer. Somebody who's good at coding, obviously. But that coding may be some domain level coding. You're creating an electrical engineering concept. You need somebody familiar with electrical engineering software. But then you need somebody with web experience, backend experience, because it's obviously a virtual simulated experience through a browser ideally. So you need people, in other words, with IT skills. Then you need people with good language skills, because you want good quality text, good quality manuals. You don't want grammatical mistakes, because the whole world's going to see your experiment afterwards. Right? So you need, if you think about it, different skills. So how to create a team is itself an interesting challenge for you. And we went away from asking kids from the same department to work together. It doesn't happen. I understand that you guys have been made to sit together as teams as instructors from different colleges. One of the reasons for that is just there's some cross-pollination of ideas. You become aware of things outside your own department. That's very important. That's hugely important. If you're going to do anything innovative, that's hugely important. So how do you create teams? Yeah, next. So yeah, if you go back. So we are currently, if you look at the 3rd National Boot Camp at Aurangabad, our model is not fixed. We are evolving. We ourselves are learning how to do these things. Right? So at this time, our structure is, we're actually taking on 30 teams, where in each team there's a faculty member and maybe 3 students. The hardest thing for us to do in a boot camp has been to get the faculty to work with the students, because there's an ego problem. The faculty is the boss, the students are just employees delivering something. The reason it's important is because it's a collaborative effort to put together a simulator. And the instructor cannot just walk up and say, here's my theory, you just code it. You have to understand the difficulties of the developer in coding the stuff. You have to understand how to make that, ultimately that whole experience more rich for the student. And if you don't yourself have programming skills, then you're dependent on team members to do it, in which case you have to collectively work as a team. So how to do that So the first day usually goes into making sure the teams work well together in our boot camps. And we end up putting pressure on everyone in the team to collectively contribute. And usually the end output is much better when the team has been carefully designed. So when you, for example, think of clubs in a college, usually it's a bunch of friends trying to hang around together to do some activity. It could be some social service or whatever. But partly the reason you're doing it is because of the fact that you're hanging around with friends. That doesn't help too much here because you want to create something of high quality, and this is not about hanging around with people. This is you offering something in terms of your skill to a team, and hopefully the others are also equally contributing their skills, not the same skill. Because the moment two people have the same skill, somebody is bored because one person is not working. Yeah, we're about to run an event in Diva Patil, and we'll let you know of this through the TechWhip office, because if nothing else, you can observe the whole process and understand what goes on, and that gives you a head start in creating your own content. For us, it's a lot of work. The event is 6 days, but before the event happens, next slide. Before the event happens, keep going. Do we have a slide on the bootcamp process? Yeah, here we are. So this is what it takes as a bootcamp. Right? Do you see the third line? Pre-bootcamp. It's one line here, but it's a huge amount of work before the actual physical event happens or content development. And over there we are explaining several things. We are explaining, for example, storyboarding. What do you mean by creating an interactive simulator? When I create an interactive simulator, if I don't want to bore you, I have to create a series of tasks which keeps you engaged. Otherwise, it's not interactive. If somebody can just keep pressing a button and things happen, that's not a big deal. Right? So how to create an interaction which is itself useful? It turns out to be a hard thing. Most of us have not thought about teaching that way. How to design, in fact, design a lecture systematically, we have not thought. So that's storyboarding. The business about Git is how do you now use technologies to store your source code. You're going to create code. How do you store it? How do you retrieve it? How do you update it? How do you keep track of previous versions? And how do you make modifications to somebody else's versions of code? So we explain that whole process, because one of the big things here is technologies change. One of the reasons virtual labs has been harder than NPTEL in terms of a program, creating the program. NPTEL, somebody gives a lecture once, you can capture it and you can store it online, and 5 years later you can come and watch it. Virtual labs, I create a simulator for a concept, I keep it online. 5 years later, operating systems have changed, browser technologies have changed, software libraries have changed, and that original source code will no longer run unless it's recompiled, updated, and refreshed. So technically it's much harder to keep a virtual labs program running over time. Okay? So we spend a lot of time on how to deal with code, how to make sure the code's reusable long term. We explain other open source technologies, JavaScript and so on. And in fact, because most people who will come into this team structure will not have been familiar with HTML, CSS, JavaScript, we actually spend some time teaching them the basics of this, both before and if needed during the workshop itself. Okay. We talk about something called Markdown, the fourth line, day one. We talk about Markdown. When you're writing code, can you write documentation for that code? Because one of the biggest problems with people writing code is the next guy who comes and reads that code doesn't know what's going on, because there are no comments thrown in on this, right? And can we actually leverage the theory manual that you want directly from this code? Can you capture the theory and have it written in the code and have it in some kind of format where it might look to you as some code written in some language, but just like HTML, you write code, when it goes through a browser, suddenly it becomes plain text as you read it, right? So do you have, therefore, the ability to use a certain typing format, a syntax format, which allows you to interpret what's been written as your theory? So that's called Markdown. So we don't expect that people know these technologies. We'll spend time with people either before or during the workshop to train them on this. But each of these things that's been chosen here if you spend some time learning these methods, it will have a lifelong effect on the way you do your research. Because it's fundamentally, if you think about it, being organized about how to maintain your codes, document your codes, update your codes. It's a process. Okay. Then days 3, 4, 5 become very specific about the artwork needed for a particular experiment, and that the team is the judge. We are not the judges. We are not experts at this. We just essentially move about motivating teams and pointing out what may be tips or practices that they can adopt from some other team. Okay. One of the reasons we run these as boot camps and workshops is, if each team were to do development in isolation, ideas don't transfer. Nothing like you developing something, then you roaming around watching another team develop its experiment, then you realize that idea is great. Can you come back, steal that idea, come and build into your own experiment? So that's why we try to do this almost like a hackathon. We do it at one shot with 30 teams sitting right next to each other, spending one whole week, and a lot more happens collectively than if you did these things individually. Yeah. So then in day 6, we actually go ahead and review these experiments. And the question is being asked, are they ready to be hosted? Are they ready to be shown to the world, in other words? Are we getting there? And one of the reasons for that is, if you try to do stuff in 3 days, like this, you do stuff in 3 days, then you go back to your colleges, your usual routine will kick in, your usual headaches will kick in, the job will not get done. Right? So how do you get the job done? And how do you get to the point where you've got high quality content, completed, reviewed, somebody tells you it's great, done, and you can leave it alone unless there's a real big bug that is noticed in your content. So we actually have realized that there's a need for a certification process, because that's a reward, especially to the students. Students, we have realized, are very enthusiastic about this, but giving them a certificate is even better. So we do that. And we actually have gold, silver, platinum developers, that sort of concept, based on the quality of what they've done and the extent to which they've continued to build beyond the initial effort. Yeah. If you go back, I think we had some. If the content is to be hosted nationwide, and by the way, I should tell you, there are colleges in Spain and in the US already using virtual labs content. So this is no longer us creating content for Desi colleges. We're realizing the world is adopting this content because we have kept it online for free. The Chinese have come up to us, have come up to MHRD and asked, can we buy virtual labs as a whole package? Okay. Answer is no. It's meant to be an Indian product. But if it is to be created in a formal sense and to be hosted, we actually realized we need to rigorously go through a series of milestones. So what happens, therefore? Whether this is now a lab from an IIT, experiment from an IIT, or from a college like PVG, there's a process. Somebody proposes to create a simulator. If the intent is for it to end up in the national bundle of experiments, then we will do a check to see whether you propose to use free software, because we will not later on spend money or time on proprietary software, because the only thing that will do is make some other company rich, when multiple copies of that software have to be sold for the lab experiments to be handled by thousands of students. It's like MATLAB. You know? Think about it. If I create simulators in MATLAB, then finally, I know we all pirate copies of MATLAB, but MHRD cannot permit that, IITs cannot permit that, which finally means for a virtual labs program to run with MATLAB simulated experiments, I have to run MATLAB on servers, for which I'll have to buy thousands of copies of MATLAB if I expect thousands of simultaneous uses. That's a big cost. So instead of MATLAB, use something else like Scilab, or implement codes in Python, or some other platform, right? So that free and open software check. Then what's the gap? Are you creating an experiment in a new concept space, or for that matter, are you trying to create a better version of an experiment that's already there? Because that's starting to happen. People, it's like an app. You're trying to download an app on a phone, and you realize there's a better app. So you're choosing, right? You're free to choose which app to download to achieve that same feature. Virtual labs is kind of getting there. What you realized is, people look at a lab experiment that's been created, and some of them say, I can do better. Then you create your own version. and we'll put it up there and let the public download whichever one it wants and use it in their teaching, right? So, but we do a gap check to see where it fits in, how that concept, who might use this particular experiment we've created. Then there's a formal review process where there's a lab development committee, usually IIT Delhi and IIT Bombay together review and approve of this. And then at this point, we don't ask you to code, so the coding will happen much later. So usually the problem was everyone jumps in and codes and creates a virtual lab, and then you realize it's all great, coding-wise it's all great, but the learning is limited. From the student's perspective, the learning is limited. So we instead first ask, what is the pedagogy that's going on? And there, if it turns out you're not actually addressing the learning levels of the students, we force people to interact with us, and then we address elements of pedagogy. Make sure that, okay, make sure that the developers have understood the basics of pedagogy. Then one of the processes we have built in is to get opinions from multiple people. It's why are we the judges of everything? We are not. So we get reviews from multiple people, including colleges like yours, and ask what would happen if experiments of this sort with these storyboards were created. Would you find them useful? And the essential reason to do this is to make sure the quality of what's created, which happens with a lot of effort for most colleges, that once it's created, it's likely to find some users. So at which point the developer comes back, so point 6 and 7. So this, you can see it's an iterative process. We're not just signing off and taking anything that anybody creates. We're forcing people to kind of come to some quality. So storyboards, review again, at which point points 8 and 9, you start creating source codes, and at this point you start uploading source codes onto a code hosting service, which we maintain. One of the reasons we are creating this code hosting services, we expect people will borrow code. If you realize somebody else has got a good experiment design, the way they are interactively explaining a concept, as I said earlier, you don't need to learn how to program it from scratch. Go take some of their code, reuse it, as long as you acknowledge it. It's all open source. And that's the philosophy of it. Okay? And then finally it goes into point 10, which we call beta hosting. What we mean by that is, instead of being world visible straight away, it's a limited visibility of these experiments to a few colleges. They use it in their teaching. If it looks like it's working well, at that point, we'll finally hand off to number 13, a central hosting service, which currently is running in IIT Hyderabad. They are the guys hosting the 1,200 experiments already created. So we are more in the development process of things. We are letting other people host what's already created. Yeah, next. So the team structure that I talked about, the way it works, the faculty is sitting on top, but the faculty ideally is sitting to the side of the 3 students in this cartoon. So the faculty is not a boss here. The faculty is somebody collaboratively working with 2 students from the same discipline and 1 student from a different discipline. I can't say that enough. You need students with different backgrounds participating. You will, in any case, in your own department, find that there are some fellows who really love to do some IT stuff on their own time. And they'll be assets to you when you try to do these things. But it's very important for you to go out of your department and engage with people in other departments and get access to students in other departments, because that's how it's going to actually take things to a different level. Yeah, next. If you look at how we did this, Gujarat University, Marwadi University, Aurangabad, all of these universities were desperate for these things to happen. So it turns out they were willing to put local funding into play to get this done. So this is not, so if you're all wondering how do you run events, how do you get things done? Turns out universities have the money, universities have the desire to do this. You just need to find a way to tap into this. You have an easier process because you are all part of a textbook program which will actually fund, you're funded at your colleges to do these things. A large part of the textbook grant which goes to your colleges is to actually run events of this sort, like boot camps, and to execute certain activities of this sort. Okay? So in that sense, you can tap into this, and we can think of boot camps later on in the year in Rajasthan. But again, it's not all about one event. Appreciate that a huge amount of effort will have to be spent in a pre-boot camp fashion. And what Pushpadeep and his team does is we run webinars all the time where we explain individual topics. What do we mean by storyboarding? What do we mean by Git? What do we mean by the use of Python for creating codes of a certain kind? And so on. So each FOSS technology that you want, we're going to have some discussions. The basics of pedagogy itself. Okay. Otherwise, we walk into a workshop like this and it's culture shock. You have no idea what we are talking about, and that's a total waste of everybody's time. Okay, remember, we are planning on approximately 30 teams, 4 to 5 people per team. That's a large number of people at an event who hopefully are productive from day one. And that only happens if a lot of time has been spent in advance. That's why I put this explicitly out there. We would be running many pre-bootcamp sessions. So the objective is, if you're interested, you come online and you participate and learn. Yeah. These slides will be shared with you, but there's a lot of material that we've been under pressure to explain our methods to so many colleges that we have started documenting these and writing these up. So in other words, you can read up these things from these links here. And there'll be announcements about webinars and so on periodically, which we'll let you know. So where does, in kind of wrapping this up, where does virtual labs finally go? If you look back, we've created simulator experiments. We have rolled them out. We've spent a lot of time with colleges with rolling them out. But we're now getting to the point where we're saying a community must be creating this content. Not only are we now saying the community knows perfectly well what it needs, but they actually have the talent to create these things. And rather than us giving them stuff, we need to work with them to create their own stuff. And better things will happen the moment we do that. Okay? We are under pressure to go national with this rollout model of boot camps. So both north and south of us. In terms of technologies, there's been some pressure on us to make sure everything is accessible simply through a simple browser. Why? Because then the browser is accessible on a mobile phone or a tablet or a laptop, whatever it is. So just make sure that people can take a live experiment anywhere, anytime, and you don't have a barrier in having to download softwares of a certain kind to run your experiments. So just like, for example, you access Gmail through a browser window, and essentially the Gmail web app essentially downloads, and then your mail starts downloading. So in a similar sense, can we push lab experiments? So browser-based technologies for the most part. And as I said earlier, the real use of a lab is not as a standalone lab. It's right next to a piece of theory. So we're already in the process of now taking some of the NPTEL courses and upgrading them into MOOCs, where we are taking bits of theory and we are inserting virtual lab experiments one at a time. So that right then and there, you reinforce a theoretical concept. And you essentially improve your learning to a higher level instead of simply recalling a theoretical concept. There's also some pressure, and we have started work on this, on tailoring labs to individual students. And what I mean by this is, the assumption, just like with learning of other forms, the assumption that every student will learn at the same speed is wrong. And we see that. When we have run experiments with virtual labs on large classrooms, there are some kids who just crack it, who know what's going on and crack it. And there are others who just struggle and take a lot of time. And we see that because why? They go back and forth. They go try to take the simulator, then they go back and read the theory. They go to the theory tab. And they go back and forth, and you realize finally that all of that behavior indirectly is telling you that they're confused. But if they are essentially wasting time, there are ways for us in an automated sense to detect that they're wasting time. I can figure out how much time is being spent on each action, for example, in that simulator. And that gives me a hint as to whether somebody is learning on a fast track or whether they're learning on a slow track. In which case, if they're learning on a slow track, I can start giving them hints, right? But that is essentially you personalizing the learning experience for a kid. So you see that, therefore, a simple simulator, as I start adding more features here, as I start keeping tabs on who's using each element of the simulator and how they're using it, I can start personalizing it to the point where it becomes an even better experience for a student. We have now started creating regional centers. PVG, for example, is a regional center. And the reason is some of these centers have just adopted the whole experience to the point where they are now going out and explaining virtual labs to the neighboring colleges. And essentially, they are taking on a role we were initially engaged in. What that does is it allows us to scale even more. So at this point, PVG takes care of activities around Pune. We have got colleges in Nagpur. Gujarat University is taking care of most of Gujarat. So we expect that in due course that as you start rolling out your own content, that some of you will elevate to being regional centers who will in turn take care of a very large zone around you and start providing support, particularly from a development perspective around you. Yeah. Just to give you a bit of a hint, MHRD is going to announce that virtual labs will formally be included in your curriculum, just like NPTEL is mandatorily a part of your curriculum. AICT and UGC will announce this. All universities will formally be required to adopt this. That's a bit of a stick, unfortunately. We don't want people to adopt it because they're compelled to adopt it. We would rather have them adopt it from the standpoint of actually creating their own training content. And in a big picture sense, that's what we want. So let me end with that thought. Virtual Labs was created by MHRD to solve a problem where it felt that lab instruction was poor in most colleges. But 5 years later, 6 years later, we are now talking about creating small simulations for use actively in an actual lecture in a classroom. So the experiments can either be done as part of a lab course, they can be done as part of a theory course, they can be done by a student on their own time. It's for us to figure out how to best use all of this content in a learning experience, right? So what we are trying to crack is the technological aspect of how to create this content, how to host this content, how to update this content. It's for you to figure out how you're going to use it in a training methodology. And we'll learn from that experience as well collectively as to how to best offer this content. Okay, we are under pressure to scale to polytechnics now, because again, that's a different kind of syllabus that they have that we need to address. But again, they could desperately use some scale up in terms of quality instruction. Yeah. And if you look at how our colleges, especially the likes of PVG and Gujarat University and so on, have evolved, they initially came to us 3-4 years back as rollout partners. They were just rolling out content we created. So that's the first point there. Then they had the courage to ask us, could they use us as mentors to create their own content? And they became developers the same way we were originally developers. To be honest, some of their content is better than our content. And that should not, in hindsight, be surprising. There's a lot of talent out there. And that talent found a way to connect with us. And we benefited because we saw that talent, which normally would not have seen inside an IIT. Okay? Some of these colleges are now going back to the original question. Do you remember my original 2 slides? Why do we run a lab? The points where we run a lab to test a concept and to gain physical experience of some hardware. In everything I've described, it's been about testing concepts, but nothing about physical hardware. So the colleges which have actually evolved over the last 5 years are asking the question, how do we now build low-cost hardware to address the second part of this? So that they can finally end up, remember that other slide, what's the ideal experiment? You walk up to a storeroom, you take your parts, you build your apparatus, you generate your data, you dismantle your setup. They want to do that. It turns out money is not the problem. It turns out sincerity and intentions are the issue for the most part. Getting approvals from maybe management may be the issue. Money has never been the problem. Okay? So they are working with us now on the creation of new hardware labs. But the same flow-through pipes, once upon a time I had to go buy pipes. I had to plug in various meters to measure pressure drops and flow rates and so on. These days, we are now talking about 3D printing a pipe. We are talking about 3D printing meters. We are talking about taking sensors available off the shelf and plugging them in using data acquisition methods which are very standard, Arduino boards for example. And we are pulling data and we are making it a much better experience for the student. In other words, 3D printing is anyway going to be the sort of thing at some point you'll be teaching your kids. And now the question being asked is, can you 3D print your lab apparatus and take things to a different level? That's not to say it's cheap, but it's much more doable than it was 5 years ago. Okay. So we're getting to that point where we're asking what's the next generation of lab experiments as hardware experiments itself. And even there you'll see the basic challenge, which is what are the scripts, what are the blueprints for various pieces of hardware that you'll want to build. And by the way, if one lab builds it, if one college builds it, how does another college benefit? So can we have some kind of a structure where blueprints are now hosted online and others can download and implement that experiment, build their own experiment. So we have started working on that. And a final point, how did I personally benefit from this? The team which originally came to me, worked with me to build virtual labs, were a bunch of diverse skill sets. We've created virtual labs, we've given it away to the community. That's social service in some sense. But then the team asked, what else can we create of value? And they realized that they were, for example, when they were building this reactor which was trying to keep online, there was an aspect of building hardware, there was a data communications challenge, there was stuff to be done with data which was streaming, so in other words, data analysis online. All of those learnings they took and said, can I apply it in healthcare? They built gadgets in healthcare, which are also remote monitoring gadgets, the same way the reactor was being remote monitored, and they've created a startup. When I tell you that, therefore, different skill sets should be brought together, it's because things which happen 5 years down the road are not things you would have planned for now. So you create clubs of people, you create groups of people, and you invest time in groups of people, and nice things will happen 5 years from now. Okay? Because when enough bright people come together, they will not only build a lab experiment for you, they'll build hardware for you, they'll build other things for you. So how do you create clubs going? So one thought is, the way IIT does this is we create, for example, we have a web encoding club. And regardless of which department a student is from, these kids hover around each other trying to learn the latest technologies in coding and in web design. And if you were to have a web encoding club, if you think about it, how much effort does it take for an instructor who has a storyboard to now create a new simulated experiment? Because you can resort to your web encoding club team to come in and create your interface for you. You don't have to struggle to find this all the time. So some investment at a college level in creating club structures, whether it is to play with coding, whether it is to play with hardware, again will pay off. That's the sort of thing you want to think of as a tech-based activity, because if I understand it right, you do have the funding available to pull this off at your colleges. Okay, so these are all different elements which, as you're all getting into college life, you might want to think about now. And while it's a lot of your energy going into keeping these things running, the payoff is 5 years down the road, 10 years down the road, and the payoff could be big for you. So I'll end with that. So thank you very much. So last slide. Just the contact details if you need these.